Hey everyone, and welcome to this crash course on the Navigation 2 stack with ROS2. Who is this crash course for? Well, if you have learned ROS2 and want to start navigation from scratch, or if you have already started with Nav2 but you feel completely lost, this is for you. It is not an advanced course, okay? It's ready for beginners or for those who want to get a good refresher of the basics. And what will you do? Well, you will first install the Nav2 stack on ROS2 Humble. Then you will start directly to generate a map with SLAM. After this, we will check what's inside the map and then use this map with the Navigation 2 stack so that you can make a robot navigate inside the map. And to do all that, you actually don't need to buy any hardware. We will use the simulation of an already configured robot, the Turtlebot 3 on Gazebo. To be able to follow the crash course, make sure that you have installed ROS2 Humble on Ubuntu 22.04. I'm going to add a link in the description to do that if needed. And it's going to actually work better if you have installed Ubuntu as a dual boot, not in a virtual machine, where you might have some issues, especially when we run Gazebo. You will also be able to progress faster if you already have some basics in ROS2, such as the command line tools, topics, and services. Now, this crash course is great to get you started, and if you want to go further and dive into more details about the Nav2 architecture, build a custom world, adapt a robot for Nav2, or even program with the stack using Python, then I have a much bigger course for you, which contains 6 hours of video content and practice activities. You can find the course link in the description below. Alright, and now let's get started with Nav2. What is the Navigation 2 stack and why do we need it? Before we get started, let's just be clear on the terms we are going to use. When I talk about navigation, Navigation 2, Nav2, well, this is all the same. I am talking about the Navigation 2 stack in ROS2. Unless I specify that I talk precisely about Navigation 1 and ROS1, then when I say stuff like navigation and ROS, I am targeting Navigation 2 and ROS2. Alright, so why navigation or Navigation 2? Well, let's take one step back and talk about ROS2 itself. Why do we have ROS and why do we use it? The main benefit of ROS is that you can create the base layer of your robotics application super fast. ROS provides a standard for robotics applications that you can use on any kind of robot, and basically this will allow you to avoid reinventing the wheel and instead work on the high-level functionalities of your robot. You also benefit from a strong open source community and some plug-and-play packages that help you to add functionalities faster. So once you know ROS, you can really speed up your development time. And you might be thinking, well, all of that is great, but from this point, how do I make a robot navigate? Because there is still quite a big gap between using ROS2 and making a robot navigate. So if you were to implement all that by yourself, it would take a lot of time and effort. Fortunately, we have the navigation stack. Here we will use the Navigation 2 stack with ROS2, which is the successor of the Navigation 1 stack with ROS1. And what is the stack, by the way? Well, it is simply a collection of packages that is designed to achieve a specific goal. And what do we want to achieve exactly with navigation? That's an important question to ask. Well, the main goal is to make a robot move from point A to point B in a safe way. So basically to find a path that allows the robot to reach the destination while making sure that it will not collide with other robots, with people and obstacles. It's quite important that you don't hurt people and that you don't damage the environment or the robot. To achieve this, we will do a two-step process. First, we will create a map of the environment using SLAM, and in a second step, we will make the robot navigate using this map. All of that using the navigation functionalities and tools, and I'm going to go into much more detail about this during the course. And once you understand how it works, you will also see that you can easily integrate the Nav2 stack in your ROS2 application. For example, from an independent Python node, you can give commands to the stack and make the robot navigate just by using the standard ROS2 communications and some simplified APIs that we will discover and experiment with. Alright, and now let's start the course and let's install the Navigation 2 stack. In this lesson, you will install the packages for the Navigation 2 stack. That's going to be super quick actually, as you will see. Just make sure that you have correctly installed and set up ROS2 Humble on Ubuntu 22.04. So if I print the end of the bash rc in my home directory, I should have this line here. Source opt ros humble setup.bash. So if you don't have this, well, please go back to correctly install and set up ROS2. And now to install the navigation stack, well, we just need to install a few packages. So we are going to do sudo apt update to make sure that we have the latest. So all packages are up to date. And so we have the more recent sources. And now we can do sudo apt install, and we will install first ros-humble-navigation2. So you can press tab, as you can see here, navigation 2. And then we will also add ros-humble-nav2-bringup. Okay, so we need those two packages to be installed, and actually those are not going to just install two packages, okay? It's going to install a collection of packages that contains everything you need in the navigation 2. And there is another thing that we're going to add is Turtlebot 3. I'm going to come back to this Turtlebot 3 a lot in this course. This is a robot. Okay, you probably already know the Turtlebot 3, but if you don't, that's simply a mobile-based robot. And what's good about this robot is they have a complete simulation already working. So we can work on the navigation and try to understand the different concepts without having to run a physical robot. Okay, we can use a simulation that's already done for us. So that's super, super convenient. So I will install with ros-humble-turtlebot3. And I'm going to put an asterisk, okay, so we can install all of the Turtlebot 3 packages. Okay, so make sure you don't forget this. Okay, so in the end, we have those 3 packages. I'm gonna press enter. And well, I have 0 new to install because I've already installed it before, but for you that's going to be probably a few hundred megabytes of packages to install. So you wait until the end, and well, that's all. That's really all there is to it. Now you have the navigation 2 stack and Turtlebot 3 installed on your computer. Before we start to use SLAM to generate a map, let's actually start a robot in a simulated world. And for this, let's use Turtlebot 3. Later in the course, I will also talk about using navigation with a custom robot. But the thing you have to remember right now, so one very important thing to have at the beginning, is simply a robot that can move in an environment using ROS2, of course, and with a teleop node or something similar that you can use to make the robot move either autonomously or with a keyboard, a joystick, etc. And well, good news for you, everything is already done with the Turtlebot 3. So in this lesson, I will just show you how to start the Turtlebot 3 in a simulated world and how to make it move. So that in the next lesson, we can do the SLAM and generate the map. And that's something very specific to Turtlebot 3 is we need to first specify the Turtlebot 3 model that we want, because there are a few models. There is the burger model, there is the waffle, and there is the waffle pie with Raspberry Pi. So we just need to specify which model by exporting an environment variable. That's very specific to Turtlebot 3. And to do this, well, I'm simply going to go to my bash rc. So you can just edit the bash rc. And you go to the end, you should have this line, of course. And after this, I will put, so after or before actually doesn't really matter. I will put maybe just before. So we have all the export before the sources. Export Turtlebot 3 underscore model, so all uppercase, is equal, and let's use waffle. So you type exactly this, export, and then Turtlebot 3 underscore model is equal to waffle. If you don't have this, then when we run the next command, you're gonna have an error saying you have to specify a Turtlebot 3 model. So let's save, okay, and you can either open a new terminal or just source the bash rc, so we have the environment variable. Okay, if I do print env and then pipe with grep turtle, you can see Turtlebot 3 model is waffle. Now we are going to start this with Gazebo. Maybe before starting the robot in Gazebo, let's just run Gazebo like this. You just run Gazebo, And well, you should have this, so make sure that you just have, well, gazebo here. You can check the FPS down there. Okay, so I have 62. If you have something around 60, or if you have something maybe around 30, that's still correct. But that's something you have to check, that you have something that works here, and also real-time factor should be close to 1. Okay, so if you have this, everything is working correctly. Let's close this. Actually, I would recommend if you close Gazebo to do Ctrl+C in the terminal, and not necessarily to close the window. That's usually closing Gazebo in a cleaner way. All right, and now let's start the Turtlebot 3 in a simulated world. So to do this, you can do ROS2 launch. So we are going to use a launch file from what package, from turtlebot3_gazebo. So here you can see we can use the auto completion with tab, and then turtlebot. So let's put auto completion as well. Turtlebot3 world.launch.py, and let's press enter. And let's wait a bit, and we have the Turtlebot 3 in this world. So the thing is, the first time that you launch it, it may take some time. It may get stuck with the orange pop-up saying Gazebo is starting or something like that. It may be stuck for maybe, I don't know, 1 minute, 2 minutes, 3 minutes. But this is normal. This is the time for Gazebo to load this world for the first time. Okay, so every time you have a new world, it may take some time for Gazebo to open it. So don't worry if Gazebo is stuck on the orange pop-up. Just give it some time, okay? Even maybe 5 minutes, 10 minutes, okay? Just give it some time. And then the next time that you run it, as you can see here, the next time you run it, so if I kill with Ctrl+C, the next time you run it, it should be much faster. All right. And so what do we have here? Well, we have the robot, Turtlebot 3 here. So that's a simulated robot, of course. Okay, a simplified version. And so on this robot we have, so that's a differential robot with 2 wheels. Okay, there's 2 wheels that are going to make the robot move. And we have a LiDAR here, you can see, with a scanner. So let's go up a bit. And you can see this blue thingy here is where the LiDAR can see, basically. So the laser scan, so you can see it has a range of, I think it's something like 4 meters. And so the range would stop here. And if you have an obstacle, you can see we can detect the obstacle. So the walls, the obstacles, everything. And so with this, we will be able to map, to create a map of this environment. And the world here, well, that's a very basic Turtlebot 3 world. That's a closed world. Okay, so the robot will not be able to go outside, just inside with those obstacles. So now, well, that's great. But what do we do with this? Well, we can make the robot move. So let's open a new terminal. And we can start a node, so ROS2 run this time, not launch, ROS2 run with Turtlebot 3_teleop and teleop keyboard. So this is a node that will allow you to make the robot move. Okay, and so you can see we have a description here that says, well, you just use the keys in the keyboard to make the robot move. And so if I press on W, you can see the robot starts to move. Okay, the more I press on W, you can see the more we increase the velocity. And we can go up to, here we can go up to 0.26 meters per second. Now if I press, so I need always to focus on this window. If I press S, I can stop. Okay, so S is a very important key to make the robot stop. Then I can make the robot rotate, okay, with A and D. So rotate on the right, to the left, and then rotate to the right. Okay, I can go, well, I can go quite fast, and S to stop. And of course I can make the robot move and rotate at the same time. So, well, I encourage you to try a bit, okay, get the hand out of it. It's not super intuitive at first, but just practice for 5-10 minutes, make the robot move a bit everywhere. What I recommend is usually I go straight. So I would go straight and I would make the robot turn just a bit, and then I would stop with S and then continue, maybe turn, not too fast, like this. Okay, stop, and then go straight, maybe turn a bit, okay. And this way I can make sure that I go everywhere and I don't bump into obstacles. Okay, because if you bump, let's bump into an obstacle. Let's go full speed into this obstacle. You can see what's happening is that, well, the robot will just have some issues and the laser scan will have some issues. Okay, so if the laser scan is not staying on the XY plan here, we're going to have some issues with the map and the localization. So let's try to keep the robot stable. Okay, and last thing is, if you want to understand a bit what's happening, let's open a new terminal. Let's do ROS2 topic list. You can see that, so here we have all of the topics running currently, and we have this command velocity. So the robot will listen to command velocity with a controller that's going to make the robot move, and then the teleop node will send a message on this command velocity with RQT graph. So if you run RQT graph, you can see, so you can refresh, you can put nodes, topics all here instead of nodes only. And you can see we have the teleop keyboard sending a command to command velocity, and then we have Turtlebot3 diff drive. That's a node that started inside the launch file, okay, that we have started for Turtlebot3. So you can see here how this node will control the turtle. And great, that's what we need first, okay, a robot in an environment, and we can make the robot move, and we have this LiDAR, okay, so we have a laser scan that we can use to create a map. And well, you are now ready to start the SLAM in the next video. In this lesson, you will see how to generate a map with SLAM using the Turtlebot3 simulation that we have just seen before. So the important thing to have right now is a robot, either in a real or a simulated world, and a way to make the robot move in the world, and that's exactly what we have. So let's start the SLAM. And first, what I'm going to do is I'm going to stop everything. So Ctrl+C in all the terminals. Okay, when you start SLAM, I would suggest that you kill all of the ROS2 nodes running and you just start everything from scratch. So here, let's open 3 terminals. On the first terminal, we are going to run the Turtlebot3 gazebo with Turtlebot3 world. So we start here again, the world with Turtlebot3. And we have this. Okay, so the Turtlebot3 starts here. Okay, so that's what we need. On the second terminal, I am going to start the SLAM feature for the Turtlebot3. And so we will do ROS2 launch Turtlebot3 underscore cartographer, and then cartographer.launch.py. Okay, so this launch file contains the SLAM feature for Turtlebot3. And we are going to also use sim time. We are going to add this argument true. Okay, so we can use the simulation time because here we are using gazebo, so we have a simulation time, and let's use this when we are running SLAM with gazebo. I'm going to press enter. And what you should have is actually so here RViz starting. So RViz is another software that's quite useful in ROS2. And you can see here we have a start of a map. Okay, so we have a start of a map that's being generated with actually the data that we have from the laser scan. You can see it matches almost perfectly. And we have a map that starts to be generated. The goal here will be to, well, generate the entire map here and to be able to save it. And so gazebo here, just to make sure that you understand the difference, gazebo is just to replace the real robot. So either you start a real robot in a real world, or you start a robot, so a simulated robot in a simulation world. So this includes all of the physics, okay, the inertia, the gravity, everything. And then RViz is simply a tool, you can see with a lot of options on the left, to just have a visualization tool for, so a 3D visualization tool. It's not the simulation itself. The simulation is in gazebo. The RViz is just a tool so that you can easily do a map, for example, easily do navigation. And you have a lot of tools that will help you during the development time of your robot or your application. All right, so we have terminal 1, we have started Gazebo with Turbo 3. Terminal 2, we have started the SLAM with RVs. Terminal 3, we are going to start the teleop node in order to make the robot move. Okay, so now we can make the robot move, and let's put this on the side. So if I press W here, so W, let's put 0.03 in velocity, you can see the robot starts to move in Gazebo, and also in RVs we can see that the robot, so we have the TFs, I'm gonna come back to this a bit later, so the transforms start to move, and the map starts to be generated with the data that we have from the laser scan. Okay, so you can go back here, and well, we can increase the speed, maybe go a bit right, a bit left. You can see when we rotate, I can stop, can rotate a bit. When we rotate, it also helps to clear the map. Okay. And so the goal here is simply to have, so I'm going to stop. You can see now we have almost so white pixels here. We have white pixels and then black for obstacles or walls, and gray is still unknown. Okay, so the goal will simply be to have everything white. Okay, so all of the free space should be white, and we should have all of the obstacles with the walls and the object in the middle. So we are just going to move the robot around, and before I finish the map, I'm going to show you, well, some of the issues that you may encounter. So let's say that you turn too fast. If you turn too fast, you can see, so the robot is turning very fast, and RVs may have some issues. So here it's still okay in this map, but RVs may have some issues to correctly create the map. So I would say don't turn too fast. Here's just because this world is very simple. Okay, so let's stop. And then let's see what happens if I bump into an obstacle. Okay? Because the map is generated thanks to the laser scan data. And the laser scan, you can see it's, if I go here, it's in a plan, it's in a 2D plan, okay? In an XY plan. Now, if I bump into an obstacle, we are not going to stay in this plan. So let's go straight. Okay, let's just bump into this obstacle, and let's see in RVs what we have. You can see the robot here will actually went. Okay, the robot is going a bit crazy now, and you can see the map. You can see the data for laser scan is going a bit also crazy. And surprisingly here, well, it's still working again, because I think this map is very simple, but for more complex maps, you can see here we have some weird data that we can maybe clean later, but for some other maps you may have some issues. So, well, I'm just gonna stop the robot here. Okay, and if you have some issues and the map is completely broken, well, you can always stop everything. So I will stop this, Control C, and Control C, and start again. Okay, so start the first terminal with Gazebo, and then start the SLAM. Have this here, and then start the teleop keyboard. Okay, so what I've shown you is just a bit of debugging, just in case later you have those issues, okay? And you can see when we start again, well, we start from the initial position here, and also the map is starting from scratch. So now let's just finish this map. So what I do usually, I will go straight, not too fast, okay? Not too fast, and I will make some small rotations here. I will turn a bit on the right, turn a bit on the left. Okay, and maybe when I'm here, I will stop. You see, I'm here, I will stop, and I will also turn a bit left and turn a bit right. You can see it's clearing the map a bit. Okay, and then let's stop and let's go straight, full speed. And okay, let's stop here maybe, and let's also turn left a bit, and stop, come back right. Okay, I'm gonna stop, and now what I'm gonna do is, let's go straight and let's turn a bit. And I'm going to finish the map. I'm just going to go through those points here. Okay, and now I have a result that is satisfying enough. Okay, so I'm gonna come back to this map just in the next lesson to explain you more about this. But you can see, well, we have white pixels here for free space, and then we have black pixels for obstacles, and gray is the unknown, so it can be the outside or it can be also the inside of an obstacle, because we don't know exactly what can be here. For example, you don't need to finish perfectly every pixel of the map. Okay, that's not really important. For example, here you can see we are missing a bit of this obstacle here, but that's really not a problem. That's not going to be a problem for navigation. Okay, you don't need to have everything perfect. If you want, you can, but that's going to take more time. And here for this map, it's quite simple map, this result is really enough. So now what we're going to do is to save the map. Okay, because for now the map is not saved anywhere, and if we stop here the slam, then, well, we just lose the map. So make sure that you save the map correctly before you stop everything, otherwise you have to do everything again. So let's open a new terminal here, and I will so I am in my home directory. Okay, and what I will do is I will create, maybe let's create a directory mkdir maps, so that when I generate maps I will just put them into my maps folder. And then to generate a map, you will do ROS2 run nav2 map server, okay, and then map saver CLI for command line interface. Okay, so ROS2 run nav2 map server map saver CLI, and then you can provide so -f, you can provide where, so the path and the name of the file. So let's put maps, let's save into maps, and let's name it my map, just like that. You don't provide an extension here. Let's press enter, and you can see this. So we should have something like this: creating, configuring, map saved, etc. If you have an error here, just run this command multiple times until it works, because it should work at some point. And now, so if I go to maps, you can see I have mymap.pgm and mymap.yaml. So we have successfully saved the map. And what I can do now is I can stop this. So Control C, and Control C, and the map is now saved.
You've already made a lot of progress. Congratulations! Now we are about halfway through the crash course. I hope that you are learning a lot, and I also hope that you like the crash course. If you find it useful, then you might want to check out my bigger Navigation 2 course, which contains more than 6 hours of structured video lessons, and which will take you much further into the understanding of the Nav2 stack. I will leave a link in the description if you are interested. Alright, and let's continue with the video.
Okay, great, we have now generated a map, but what exactly is inside this map? In this lesson, I will show you the most important things that you need to know about the map. So we have, I'm going to open a file manager, and in maps we have saved our map, and we have two files. First, you can see we have a PGM file, which actually you can see that's the image for the map. Okay, and so we have three different colors here for the pixels. We have white, we have black, and we have gray. So white means free space, black is an obstacle or a wall, so something you cannot go into, and gray is unknown. So as you can see, everything that's outside is unknown, we don't know what's behind those walls, and everything that's also inside the obstacles is unknown. Okay, so this map is going to be loaded later on when we run the navigation, and we can use this to actually find a path to a destination easily. So we have this image file, and then we have a YAML file. So let's open with Gedit, for example. And in this file, we have several information. So first, image is, well, the path, so the relative path to the image file. Then the mode of the image, well, not very important here. And then the important parameters here, we have the resolution. The resolution here is in meters per pixel. So you take 1 pixel here, 1 pixel, and it's 0.05 meter, so which means 5 centimeters. So for each pixel of this map, we have 5 centimeters. So we have a 5 centimeters precision. So is it a lot? Is it not a lot? Well, it depends. Here, when you are doing navigation with a mobile robot, 5 centimeters can be really completely enough. Think about when you move yourself inside a flat or in an office, when you pass through a door, you probably don't try to pass as close as possible to the door. You just give yourself some margins. Maybe, I don't know, 10 centimeters, 15 centimeters on each side. Okay, you don't try to be as precise as possible. You just give yourself some margins and everything works fine, okay? So 5 centimeters for navigation, well, it depends on the cases, but for this case and for most of the basic cases is gonna be enough. And also, of course, the more you increase the resolution, the more computations you will have to do. So that's a trade-off to think about. But for now, 5 centimeters is enough. Then we have the origin, which is the coordinates of the lowest left point on the map. So here in this map, in this image, we take the lowest left point here. And well, if you remember, the robot, actually the initial position started around this position here. And actually the image was rotated like this. So the lowest left point on the map is still actually this one, okay, because I rotated the image. And if you remember, also the X was pointing forward and the Y was pointing 90 degrees to the left. Okay, so we have the X axis here and the Y axis here. If we take this point and we go minus 1.24 on the X axis, we're gonna arrive somewhere here. And then minus 2.39 on the Y axis, we're gonna arrive right here. So basically it's the link between this point and that point where the robot started. So that's the origin of the map. Then negate is 0 here. If you put 1, that's gonna simply negate, so inverse all of the values. So everything that's white is going to be black and everything that's black is going to be white. Not very useful in our case. And then this occupied threshold. So the thing is, we have here a clear separation between, so that's black or that's white. Okay, so black is an obstacle, white is free space. But in the end, it's all about probability. It's about the probability that one pixel is occupied or not. And so here, the setting is that if a pixel has a more than 65% chance, so probability of being occupied, then it is considered as occupied. If the probability that the pixel is occupied is less than 25%, then we consider the pixel as not occupied. And in the end, also here you can see that, well, those values that we have here are simply, so each pixel is going to be a shade of gray, so from complete black to white, and each pixel will be a value between 0 and 255. And so if a pixel is more than 65% into the black direction out of those 255 numbers, then it's going to be occupied. If it's less than 25% out of those 255 values, it's going to be not occupied. Okay, so you have some infos about what is the map. I would say here the most important information to remember is this resolution thingy here. And one other thing we can do, so let's just open the map. So let's open my map.pgm with nano to see actually what's inside. And well, we have a lot of characters that are actually the image, but at the beginning you have something like P5, and then you have this, which represents actually the number of pixels of the image. So it will be like this original image. So we have 124 pixels on the X and 116 on the Y. So now if you multiply, let's multiply the number of pixels, so 124 multiplied by 0.05, that's the resolution, which means that the map is 6.2 meters long here, so including the gray area, and is, so let's do 116 multiplied by 0.05 is equal to 5.8 meters. So you have the exact dimensions here of the map. So if you want to know the dimensions, you can compute it like this easily. You find the resolution, you find the number of pixels, and then you can just multiply them, and you have the dimensions in meters. Alright, so that's pretty much it about the map. You don't need to understand everything right now. It's just a help to, well, to get some ideas about what you just saved. And now this map is very important because that's what we're going to use as a base to navigate in the next section. And before we get started here, there is a quick fix we need to do. The thing is, there are still some issues with the navigation to stack on ROS2 Humble. In the following lessons, when we load the map with the navigation stack, it may happen that the map is not loaded correctly or not loaded on time, and this will prevent you from going further. I have personally experienced those issues and have found some fixes on the wonderful internet. And well, I'm gonna show you that now, so you won't have to bash your head against your computer in the following sections. I have done that for you already. So make sure you watch this video until the end and make sure you do exactly the same steps as I do. We actually have two small things to do. First, we are going to change the DDS from fast DDS to cyclone DDS. To make it quick, ROS2 communication is based on DDS, and I'm not going to explain DDS here. You can check that on your own if you want to, but that's not really important for this course. What's important is to use the right one that will allow us to make the navigation to stack work correctly. So to install cyclone DDS, we will do sudo apt. So you can do a sudo apt update first. Okay, and then you can do sudo apt install ros-humble-rmw-cyclone DDS-cpp. Okay, so you can press tab for auto completion here, and let's install this package. So for me, it's already installed. I've done that previously. For you, it's going to install the package. And then once the package is installed, we actually need to tell ROS2 to use this DDS. And to do this, we need to export an environment variable. So instead of doing this for every terminal that we use, let's actually go to our bash rc. Let's edit the bash rc. And here we have, so we already have an export for the Turtlebot 3 model. We have a source for the global ROS2 installation. And well, let's just add an export here. Okay, let's put all of the export before the source. And we can do export. So you type exactly this, and then uppercase rmw_implementation. Make sure you have the exact same thing, is equal to rmw_cyclone DDS_cpp. So export rmw_implementation is equal to rmw_cyclone DDS_cpp with all underscores. You can save the bash rc, and then we're going to close this. So basically there was an issue with the map and the navigation that is not correctly working with the default DDS for now for ROS2 Humble. The fix is to change to cyclone DDS, which makes things work much better. And the second thing to do is to modify a parameter file where the Turtlebot 3 navigation package is installed. So clearly that is far from ideal. And if you upgrade this package with sudo apt upgrade later on, you will maybe have to do this step again. The thing is, this fix is probably temporary. We just need to do it until they release a version of the package that will work correctly. So let's clear this and let's go to /opt ROS Humble. So this is where ROS2 Humble is installed. And if you want to get access to parameter files for different packages, you need to go inside the share folder here, and you will have, well, you will have all the packages that you have installed. And now we can go to, so we can do cd turtlebot 3 navigation 2. Okay, So now we are in the package of navigation 2 for Turtlebot 3, and you can see here we have launch folder. You can find the launch file here, also param, so we can go to param, and we have the different parameter files, so YAML files for the different versions of the robot. And the one that we are using is waffle.yaml. So we are going to edit this one. And to edit here, you need to actually use sudo, okay, because we are not in our home directory. So sudo gedit, for me, you can use whatever text editor you want, waffle.yaml. Okay, and you will search for robot model type. Okay, so you can do Control F to search for robot model type, and we are going to modify this one. And so here, if you have differential written like this, you need to modify it. We will actually use, so what I can do is just comment like this. Okay, you can add this sign to comment the line, so you just keep it just in case you want to go back, and you just modify then to nav2 underscore AMCL, and then colon differential motion model, like this. So nav2 AMCL all lowercase, colon with, and then uppercase D differential, uppercase M motion, and uppercase M model. If you already see this here in this file, then that's fine. Okay, you can just continue without modifying anything. But if you don't see this, then please modify this line, okay? This is a fix that also I found on a GitHub issue relative to this Turtlebot 3 robot. So you can save, okay, make sure you save the file, and make sure you have exactly written the same thing, okay? That's very important. If you have one typo, that's not gonna work. And then you can close. And what I really recommend you to do, so first you can close the terminal and open a new one, but what I really recommend you to do now is to reboot your computer, okay? Make sure you reboot so that, well, you can be sure that everything is gonna work correctly. Let's now make the robot navigate using the map. We will continue with our Turtlebot 3 example here. And so to start the navigation to stack to make the robot navigate, we first need to start the robot. So we are going to do ROS2 launch, Turtlebot 3 gazebo, and then Turtlebot 3 world.launch.py. So this, we have done it previously, also with the slam, okay? That's the first step you need to do always. So we start the robot. It's going to start the robot in the world. Okay, so we have the world here. We have the robot, we have the LiDAR with the laser scan, that's correct. Okay, so everything works correctly. Now we go back to the terminal. Let's open a new terminal. And here we are going to start the navigation for the robot. So to do this, we are going to do ROS2 launch and Turtlebot 3 underscore navigation. So underscore navigation 2 actually, and then navigation2.launch.py. I'm going to explain this launch file a bit later in the course. So this launch file will contain all of the things you need to run navigation for the robot. And then we are going to also use, use sim time with colon equal true. So we use the simulation time because, well, we are using gazebo, so we are using a simulation. We want to also use the simulation time for this navigation. That's gonna work better. And then there is one thing we need to also do is to provide the map. Okay, because, well, we have saved the map in, so if I open the file manager here, in maps, we have saved the map. So we want this one, the Turtlebot 3 world map that we have called mymap. Okay, mymap.pgm and mymap.yaml. So what we need to do is we need to give this map to the navigation. And to do this, we simply add another argument, map, colon equal, and we just provide the path to the map relative to where we are right now. So maps, you can see we can use auto-completion, my map dot YAML. We're gonna put the YAML file. So ROS2 launch, and then we go in the package Turtlebot 3 navigation 2. The launch file is named navigation2.launch.py. We put the parameter use sim time to true, and then map is the YAML file that we have created. I press enter, and let's wait a bit. So it's going to start RVs like this, and you can see here, well, what do we have? We have the map here. So that's the map that we have generated, okay? That's the image that we have generated with here the origin of the map as specified in the YAML file. And so if you start RVs, and if you don't have the map, so if you don't have this image here right now, well, what you can try to do is to stop and start again. So to stop and start, I recommend that you don't just click on the button here, but yet you do Control-C directly inside the terminal. So you could Control-C here, maybe Control-C here. You can restart the terminals, maybe restart your computer. So just do those steps if you don't see the map right now. But when you see this, then that's correctly working. And what we need to do first in navigation is to actually give a 2D pose estimate. So we need to tell actually to give an estimation of where the robot is in the map. So if we go to Gazebo, well, Gazebo is the real world, the real robot. So you know where the robot is. It's here, okay? It's been started here. And in RVs, you just have the map, but you still don't have the robot exactly. You don't know where it is, okay? So we will need to click on this 2D pose estimate. Okay, you click here, and then you can click on where the robot is. So let's check. The robot is here. And so for this case, that actually corresponds to roughly about the, well, this point here, the origin of the map. That's the same point. So we click and we maintain the click, and you see we have also an arrow to provide the orientation. Okay, so the robot is actually looking forward, so we're gonna put the orientation like this. If the robot was looking to the left, we would put the orientation like this. Okay, so we put the orientation like that, and you should see something like this. So what's happening now is we have said in RVs, so where the robot is at this moment. So then the navigation is going to, well, localize the robot here, and thanks to the data that we have, so thanks to this laser scan that we have, the robot is also going to match, you can see, with this small rectangle here, is going to try to match the environment, and so when the robot moves, the robot can localize itself in the map. Note that, for example, if I put a wrong 2D pose estimate, you can see now it's like we have said that the robot is here, but you can see the laser scan data. This corresponds to the laser scan data from the reality, does not correspond to the map. Okay, so if you put a wrong 2D pose estimate, that is completely wrong, here it's completely wrong, then things are not going to work. So you need to try to be as close as possible to where the robot is. So I can put back the pose estimate right here. Okay. And now you see that I have messed the map a bit. Okay, so if you have this, well, you could restart, but also know that when the robot will go around this area, it's going to also automatically clean the map. And well, about this is the global planner here. And this is what we call, so it's called the controller, but I'm also calling this the local planner. And I'm going to explain this in much more details in the next section. Okay, so here we are going to just understand how to work with it. And you're gonna maybe understand some things with intuition, but you will not understand everything right now. And in the next section, everything will make more sense because I'm gonna come back to each component here with much more details. Okay, so once we have given the 2D pose estimate, we can easily see, as you can see with this rectangle here, so with the controller, which is the local planner, we can see that things match, okay? You can see the edges match, the obstacle here match. So what we can do now is to give a navigation goal. So let's say we want to go to this place right here, so we click also and we maintain for the orientation that we want to give. So I click, and you can see the robot will start to move. And if I go to Gazebo, the robot is moving. So the real robot is moving to reach the destination. And on RVs, you can see we can follow. So you have this pink line and this blue, this small blue line also that's following the goal and trying to reach the goal. And then you can see it's going to turn to reach the orientation that we wanted. And then, well, that's it. the goal has been successfully reached. And so just a quick note on the coordinates, you can see that we always have this red, green and blue coordinate system here that's also here in Gazebo. So the red is here, the green is here and the blue is here. That corresponds to the right hand rule, okay? So in red we will have the X pointing forward, and then 90 degrees to the left we have the Y, okay? So this makes a plan, okay? So that's a 2D plan here, X and Y, and then we have the Z going up, okay? So if you put your right hand, you're gonna see easily with 3 fingers, that's the coordinate system that we're gonna use, and you can see that's the same thing here for Gazebo, for RVs, and everything we do later, okay? And also in the next section, I will give you more explanations about those coordinates here. Why is this coordinate here, that one here, those ones there, okay? You will understand this better. So now what you can do, well, you can just give another navigation to goal, and you can see the robot will move, so it will turn, it will move autonomously, okay, while avoiding, you can see those fixed obstacles, and making sure that you see it doesn't go too close to the obstacle or to the wall, okay? So you have navigation working. And now, well, let's say that I give a goal that is not valid. So let's say I want to go not here, but I want to go here. What's gonna happen? Well, you see what's gonna happen is that, well, we don't have a line here, and the robot is gonna be stuck and try to move a bit. Okay, so if we look at the terminal, we have, well, we have some recovery behavior that I'm gonna explain also in the next section. So the robot is trying different things to, well, to clear the space. Maybe actually there was something on the map here that was recognized as a wall, but that is not. Maybe there is an obstacle that we can clear. Maybe there is a different path to go to. But in the end, if the robot doesn't find any possible path, then you can see here we have the feedback aborted. So the goal was aborted, okay? If I do here a very simple one, you can see the goal will be reached. So reached, succeeded. And if we try to give a goal that can't be reached, the robot will maybe try to go, but then the navigation to goal will be aborted. All right, so try to give a few goals. And one thing is that if you are starting, if you want to start again, you can start again. So you can do Control-C here. So it might take some time, so you just do Control-C and you wait. And then you can start again. You may want to also restart Gazebo, but here we don't really need to. I have the RVs here, and we also, so you can see we need to give the 2D pose estimate again. But this time the robot is not here anymore. The robot is there. Is there and pointing towards this direction here, okay? So we need to give a 2D pose estimate. That's about, so you don't need to be super precise, but something like this. Okay, and the robot, you can see, will try to match. So you can see I didn't match exactly, I didn't have exactly the right position, but the robot will try to match as close as possible to the map. And now you can see if we give a navigation to goal, also things should start to be put back in place. Okay, so you can see the map also is coming back to the right place. Okay, and now the robot is here, and the robot should be, well, here. So to conclude here on this lesson, well, you need to start first with 2D pose estimate once, and then you can give some navigation to goals. There is a nice and very useful functionality in navigation 2 that you need to know, and this is the waypoint follower. So let's say you want the robot to go through different points. Okay, you want the robot to do a turn around those 4 blocks, for example. You could put a navigation goal here. Okay, so the robot will follow this path. You can see the robot moving in Gazebo as well. here. And then once the robot is there, you would give another goal to reach this. And then another goal to reach, for example, this position with this orientation. Okay, but the thing is, you can actually give those goals, so the 3 goals or more goals, all at once if you want to. Okay, to do this on RVs, you can click here on the left, you have navigation to, you can click on Waypoint Nav through Poses mode. So once you are in this menu, you don't click on anything here, you just click on navigation to goal and you put a new goal here. And you can see now we have an arrow. So waypoint 1. And then let's put another one, for example here. And let's put another one, for example, where the robot is, like this. So we have 1, 2, 3 waypoint. And we want the robot to go through all those points. And now we can click on Start Waypoint Following. You click here and you see the robot will first go to the first waypoint. And then the robot reaches the waypoint. You can see it will reach the goal. And once it reaches the goal, it will immediately start the second waypoint. And then the third waypoint. And the path is completed successfully. So we have been through 3 different waypoints. You can add as many as you want, and the robot will go through the waypoint. There is another mode that you can, so you can click also here on waypoint here, and instead of clicking on Start Waypoint Following, you can click on Start Nav through Poses. This one will try to create a path that goes through all of the waypoints, but without stopping. So this can be quite useful if you want to go a bit faster, but note that this feature is not as stable as the waypoint following, so the normal one where you go through each one by one. Okay, so let's try this. And actually, well, we have an issue here already, so the robot cannot find the path. Let's cancel. Let's just click here and click on Cancel Accumulation. Let's just give some poses here. So 1, 2, and then 3 like this. And let's try again, Start Nav through Poses. And you can see it should try to just do everything without stopping. So if we look at the robot here as well. Okay, and we have some issues here. I don't know exactly what's happening because the path is changing, and well, this functionality is not as stable as you can see. So sometimes it works, well, sometimes not. I don't want to just show you a case that works and then tell you that it's going to work every time. Actually, I'm just showing you that this Start Nav through Poses is not the most stable feature. So you might choose to start a waypoint following, so the robot is going to stop at each point, but you can just give kind of an array of points and make the robot follow this. Okay, so now you can practice a bit on your own, try to make the robot go through different paths, through different waypoints, okay? Experiment a bit with those options here.
Alright, and that's the end of this YouTube crash course. I hope you could learn a lot and get a better understanding of what is the Navigation 2 stack and what you can do with it. So you have seen how to get a hand on Nav2, but now comes the most interesting part, which is to get a full understanding of the architecture behind Nav2 and to be able to use Nav2 for your own project, which means, for example, to create your own simulated worlds, to use the navigation with a custom robot, and to make the Nav2 stack work with an existing ROS2 application. And that's exactly what I cover in this much bigger course, which contains more than 6 hours of video content. And let's have a quick look inside. So here I'm inside the course, and as you can see, we have 9 sections in total for 6 hours of content. And well, the first section we install ROS2, we install navigation to stack and some tools. So this you've already done. And then we have two sections where we actually do SLAM, okay, to generate a map. So you can see we make the robot move in the world, that's what we've done. And then we generate the map. We have an extra activity here, okay, and we make the robot navigate, and we have also extra lessons and extra activities to practice on this. But then the interesting part here, the really interesting part is this, understand the navigation to stack, okay? So we have 40 minutes of explanations here to understand everything that's going on in the stack. After this, you build your own world for navigation, so you will learn how to use the Gazebo building editor to create a complete customized map so that you can make your robot navigate inside a custom map. And then, so you can see we have more activities as well. And then I'm gonna talk about how to adapt a custom robot for navigation too. Okay, this is going to be kind of an introduction, but still 1 hour introduction to explain to you all the different steps that you can do here. And finally here, we will interact programmatically with the navigation stack. So you will learn how to do, well, what we did in RVs. Okay, if you remember, we have clicked on some buttons to do the 2D pose estimate and to give a navigation goal. But here you're gonna do that directly from your own code. So you can completely integrate the navigation to stack into your existing ROS2 application. And so with this course, not only will you get a much better understanding of the stack, but you will also build some experience thanks to a lot of practice. Alright, now thank you for watching, and I hope to see you in the course.